Hello. For subject DMCG 3613 Fluid Mechanics 2 from Dr. Faisal bin Wasbari, we have to do the video presentation about 3D flow flat plate. We from Group D Section 5. For the leader, Siti Maimunah binti Zamri, B0419100034, doing PowerPoint, Introduction, Theory and Objective Presenter. For the members, first Kelvin Wong Y Hong, B0419100191, Analysis CFD, Mass Presenter. Second, Muhammad Zuhairi bin Muhammad Azmi, B0419100026, Geometry, Detail and Dimension. Method for Setup and Result Presenter. Third, Muhammad Aizad Irshad bin Zaini, B0419100101 as Video Editor. For the introduction, for such bluff bodies, the transit three-dimensional wave formation phenomena can be analyzed to understand other complex flow configuration. The flow past a flat plate in addition. This has a fixed separation point where the Reynolds number only play a role in the transition of the flow from laminar to fully turbulent. Transit force convection heat transfer from a fixed semi-inflated flat plate situated in a fluid which at large distance is moving with a constant velocity parallel to the plate. Both the fluid and the plate are initially at a constant temperature, and the transit are initiated when the zero heat flux at the plate is suddenly changed to a constant value. The thermal boundary layer equations are solved using numerical technique to extend a series which is valid for small time and describe fully the development from the initial unsteady state solution small time to ultimate steady state solution last time. Two-dimensional 2D and three-dimensional 3D numerical simulations are carried out from uniform flow past a normal flat plate with two semicolons and to investigate the three-dimensional effect of the wake flow behind the plate. A drag force element decomposition analysis is conducted. For the result obtained using 2D and 3D simulation, it is found that although the time average weight flow obtained by using 2D and 3D simulation are different, the relative difference of their contribution to the time average drag coefficient is only 10%, while the difference comes mainly from the contribution of the Reynolds shell stress. The three-dimensionality of the wake flow is further investigated using Caudron and the Lumley triangle analysis of the Reynolds stress. The span-west spectral scale of the streamwise vortices are quantified using Hilbert transform along the span-west direction. The flow over at plate at a Reynolds number of 750 is numerically investigated via fine large eddy simulation (LES), first at normal uh, 90 or tax degree and then at amplitude 45 tax degree incident flow direction with a uniform steady inlet. The effect of Reynolds number Re such as the largest of Re, the thinness of boundary layer among the plate at the X location. Simplified treatment of boundary layer heat transfer split the boundary layer into an upstream laminar section and downstream turbulent section. Heat transfer coefficient in a laminar boundary layer is strongly sensitive to the upstream history of the flow, including both the leading edge configuration and any variation in wall temperature. Consider a steady three-dimensional boundary layer flow of an incompressible dusty fluid over a horizontal stretching sheet embedded in a porous medium. Numerical computation has been carried out in order to study the influence of different parameters that describe the flow and heat transfer characteristics of dusty fluid. The theory about this 3D flow flat is first, steady 3D boundary layer flow of a compressible fluid past a flat plate with parabolic leading edge. It is derived in paraboloid coordinate for steady flow of a compressible fluid of variable viscosity past an insulated flat plate with parabolic leading edge when fluid velocity at infinity is constant and parallel to the axis of the plate. Second, 3D effect of the flow normal to a flat plate at a high Reynolds number. It is based on the height of the plate and free stream velocity. 3D simulations are carried out with large eddy simulation (LES) method. Third, steady 3D flow of a second-grade fluid toward a stagnation point at a moving flat plate. Base equation governing flow and heat transfer are reduced to a set of ordinary differential equations by using the appropriate transformation for the velocity component and temperature. Lastly, direct numerical simulation of non-equilibrium 3D turbulent boundary layer over a flat plate. Shear-driven 3D turbulent boundary layer owing to a sudden imposition of a surface span-wise velocity largest surface span-wise is twice the free stream velocity comparable to maximum value of the spinning cylinder experiment. The objective of this 3D flow flat plate is to do simulation about the meshing inlet, outlet, and boundary meshing method in the 3D flow flat plate and related the simulation with the theory in 3D flow plate.
I will be explain about the geometry detail and dimension. As we can see, this is the top view, and this is the left view and the right view, and this is the isometric view. And the dimension for this CFD geometry is the height is 20 mm and the width and length is 1000 mm. And we use the software SolidWorks to draw this geometry.
Hello everyone, I'm Kelvin. I'm going to present the part of meshing. Here we go. First, we're going to create the name selection, which the side of the object we name is as inlet, and the bottom of the object we name is as outlet. Due to some technical problem, you may not see the function that I click, but I will tell you what I'm going to do now. Beside that, the four of the surface that I just selected, I'm going to name it as a symmetry. After naming the three part, I'm going to select the tree of name selection we just do this now to make it invisible first, so that we can see the plate inside the object. We're gonna name this plate as name this surface as the plate. After that, we're gonna select all of the surface of this object and apply it on a geometry. After select all of the face, we apply it, then it should be okay. We just uninvisible all of the surfaces now. After name all the selection, we're going to the mesh part. Okay, we're going to set the mesh sizing to uniform, which means that the capture curvature set to the no also. The quality, we're gonna use the smoothing, the high smoothing. After that, the inflection, we're gonna choose the smooth one, and the automatic inflection we choose all the face that we chosen just now, which is the plate surface. And also we set the maximum layer to 10. After that, we're gonna right click the mesh. We are inserting the sizing. Due to the technical issue, it show up what I'm doing just now. After click the sizing, we're gonna choose the scoping method to name selection. And the name selection which is the plate one. Alright, After that, we set the element size to 0.1 meter, and then we're gonna to generate mesh it, and let's see the result first. We can check the quality using the mesh metric. By changing the mesh metric to orthogonal quality, we can see the result of the object, the meshing part. We can see that the quality is still extremely poor. Since the quality are still extremely poor, we click the meshing by raking it. We insert the metal, which the metal is by After insert the metal, we choose the metal which the tetrahedron element metal to the world domain by selecting the geometry section, the world body, and insert the metal tetrahedron. After generate the mesh again, we can see the result. The quality are still poor. Since the quality is still poor, so we're gonna to reduce the element size to smaller a bit on the flake sizing. We change the element size to 0.05 meter, and we generate the mesh again to see how the quality it is. Now it become better, but it's still not good enough to use that. So we're gonna to set the element size furthermore to small a bit, which we set it to 0.005 meter, which means is 5 mm. After that, we just generate the mesh. Let's see the result. How is it? Okay, now we can see that the mesh quality is good enough. Therefore, furthermore, we use the function distract the object into the half and view the plate inside the object. Now it's going the quality. It looks good, right? So here is the meshing part for me. Thank you.
I will be explain about the setup process 3D flow plate geometry in CFD Fluent. First, we need to set the time to transient, and then we click on check. As we can see in the console, we can see the minimum volume and the maximum volume for the volume statistics. And then we click on the report quality. After the report quality process done, we can see the mesh quality, the minimum orthogonal quality. And then we click model and click in the viscous model. And then we change the model to K epsilon to equation. And then we change the K epsilon method to realizable. And then near wall treatment to scalable wall function. And then we click OK. In the material section under fluid, and we click on air, we change the density to ideal gas, and then we click on change and create. In the boundary condition section, we need to set the inlet velocity to 20 meter per second. And then we click OK. And then we need to set the outlet gauge. Firstly, we click on the outlet in the boundary condition, and then we need to change the gauge pressure to 1 atm, which is convert to the Pascal unit 101325 Pascal equal to 1 atm. And then we click OK. In the preference value section, we change the compute from, we change to the inlet, from inlet, and we check the area and the length to same with the geometry dimension. In the method section, in solution method, we change the scheme to couple, and then we change the momentum, turbulence kinetic energy, turbulence dissipation rate, and energy to second order upwind. And then we need to insert the drag monitor. We change the name to drag coefficient, and then we insert new and force, and we choose drag. This error come out because we already has the drag coefficient and then under initialization we change the initialization method to hybrid initialization. And then we click on initialize. After the hybrid initialization process complete, we need to save every time step. In order to do that, we click on calculation activities in the autosave every time step. We set to 1. And we need to set the time step, number of time steps and iteration. The time step size in second we change to 0.005 and the number of steps we set to 400. And then the max iteration or time step we set to 40. And we click on calculate and we wait for the result to come out. The calculation process in the setup section is completed. We can check residuals and convergence. What is meant by residuals is residual is one of the most fundamental measures of an iterative solutions convergence, as it directly quantifies the error in the solution of the system of equations. In a CFD analysis, the residual measures the local imbalance of a conserved variable in each control volume. And then we can check the drag coefficient graph. What is meant by drag coefficient? In fluid dynamics, the drag coefficient is a dimensionless quantity that used to quantify the drag or resistance of an object in fluid environment, such as air or water. It uses the drag equation, in which lower drag coefficient indicates the object will have less aerodynamic or hydrodynamic drag. After that, we click on the result, and then we need to insert a plane bisecting plate by click on the location and then plane, and we can see this interface, and then we change the value of Z to 0.5 meter, and then we click apply. After that, we insert pressure and velocity contour by click on the insert contour, and we can see this interface. We need to change the location to plane 1 and variable to pressure and velocity to get the pressure and velocity contour, and then we need to change the range to local, and the number of contour is 150. After we click apply and we do the velocity contour animation, and as we can see, this is the result of the velocity contour animation. And what is meant by velocity contour animation? This velocity contour is a method of measuring stream discharge, in which point velocity measurements are translated into average cross-sectional flow velocities. By considering the point velocities, these averages are then multiplied by the areas of the cross-section to give the discharge.
Based on the height of the plate and free stream velocity, 3D simulations are carried out with Large Eddy Simulation (LES) method. The results we obtain from the simulation are as follows. The blue colored contour shows the lowest velocity, while the red contour shows the highest velocity. The highest velocity is 2.079 meter per second. The velocity of fluid The highest velocity is 2.079 meter per second. The velocity of fluid in the figure shows steady 3D boundary layer flow of compressible liquid past the flat plates form parabolic leading edge. Derived in parabolic coordinates, a steady flow of a compressible fluid of variable viscosity past an insulated flat plate with parabolic leading edge when fluid velocity at infinity is constant and parallel to the axis of the plate. That's all from us. Thank you for watching and have a nice day.